that's a textbook. It's a required textbook because there will be a lot of things we're going to cover in the semester are from this book. And there's a newer version, but I don't think it's necessary to get the new version. This one, if you got a used one, I think it's probably somewhere around 70, 60, 70 bucks. The new ones are 120 or something. But the newer version, as probably fourth edition, will be like 200 bucks or so. It's way bigger than this one. It's not necessary for this class. So I printed out some of the pages for today's class. So let's look at the differential nonlinearity of the DACs and ADCs first. So we can evaluate the performance of the DAC and ADCs. That's how you evaluate it. First, differential nonlinearity, or DNL. It's defined as the actual increment height minus the ideal increment height. So for the DAC, think about it. For the DAC, ideally, what's the increment height for every single digit? So DAC, you have digital input and analog output, right? If I change the input from 001, if it's a 3-bit DAC, to 002, what? To 010, right? There's a 1 LSB change increment. So what would you expect as the output? If it's a 5 volts reference voltage, it's going to be 5 over 2 to the third, right? That's, or you can say it's 1 LSB. It's 1 LSB. It's not always the case, right? So that's why you have a DNL. So look at this curve. It's on page 942 on the book. Okay. And so look at this curve. That's a digital input. That's the analog output. And there are fractional numbers because this is VL over VREF. It's never larger than 1. So they're from 0, 1/8 until 8/8. Right? And that's the ideal curve. Ideally, it should be like that, but actually it's not. So these are the actual outputs for each input. And you can see that the dots here are not necessarily on this ideal curve, so they are moving up and down. So one quick question, is that possible that the dot is moving left and right? Is that possible? Why? Yeah, there are digital signals input, right, from the customer, from the user. They are definitive inputs. So 0, 0, 0 is 0, 0, 0. It will never be changed. But however, the output can be changed because of the nonlinearity here. So the way you are finding out all the DNLs, so the DNLs is not just one DNL. For every single input, it has a DNL. For example, this will be DNL 0, DNL 1, DNL 2, DNL 3. But you can see this point perfectly matches the ideal curve. So the DNL 0 will be 0. So there's no error. For this one, it's also 0. It's supposed to have 1 LSB here. So for DNL 2, it's also 0. But for DNL 3, it's not 0 anymore. So trying to recall the definition of DNL. It's an actual increment height minus the ideal increment height. And ideal increment height is always 1 LSB. So it's easier to remember, right? It's always minus 1 LSB. So it's just looking at the actual increment height at this 3, the number 3, or point 3, right? So it's DNL 3. So the actual step height is from here to here. So if it reaches this point, it's 1 LSB, and now it's halfway of the next LSB. So it's actually 1.5 LSB here. I know it's not accurate, but just assume it's half. So it's 1.5 LSB for this actual height, and minus 1 LSB will be 0.5 LSB. So that's the DNL at this point, or you can say it's DNL3 is 0.5 LSB. Differential nonlinearity. Yeah, you can understand it that way. Yeah. Just errors. It's just errors. It's just meant you are supposed to get this point, but actually the output is a little bit higher. Sometimes it can be lower. So that's the errors. Because all the circuit components are not ideal. They have tolerance, like resistors, like plus minus 0.5% or something. And now look at this one. So that's 0.4, right? 100 is 4. And apparently it's not 1 LSB for the step increment height. So it's 0.5 LSB, and you want to minus what? Minus the ideal step height, which is 1 LSB. So it's going to be 0.5 LSB minus 1 LSB will be minus 0.5 LSB, which is DNL 4. So it can be negative sometimes. Now let's move forward with this one. So the step height here is 0.25 LSB. Again, it's not accurate, right? There's no label, but we're assuming this is 0.25 LSB increment. So,
What are those values based off of? How are you finding those values?
These ones, yeah. They are given. Yeah, it's difficult to label it, to have like divided into four pieces. We're just assuming this is 0.25. So this increment height is 0.25, and always for DNL, always minus 1 LSB, so you are getting a negative 0.75 LSB for the DNL at 0.5. So it's DNL 5, it's going to be minus 0.75 LSB. Okay. And next, we got a huge step here, and it's labeled as 1.75 times of the ideal height, right? So this one will be 1.75 LSB. And if you're looking at this point, it is at number 6. So DNL 6 will be 0.75 LSB. And for the last one, DNL 7 is perfect. So it's 0 LSB. Clear? So we have 4 different calculations for DACs and ADCs, and DNL and INL for each. So totally 4. And now we are done for 1. Pretty simple, right? Now move forward for the second one. So you can even plot it. So if you have all these DNLs at different points, you can plot and see what are the DNLs are distributed for every single point. And yes, you can say that the DNLs at each point, you know what are they, but overall, you can also, after you find out all the DNLs for each point, there will be a DNL for the overall DAC. If you build a DAC, the overall DNL will be the maximum DNLs you find out for all the points. Will be the worst case scenario. So for this DAC, for example, what's the DNL? I'm not asking for a DNL for every point. So the DNL, the overall DNL for the DAC, what is it? It should be a plus number and minus number. So a positive number and negative number to describe it, right? So what's the DNL for the DAC? Plus minus 0.75 LSB. People ask you what's the DNL of the DAC, and that's the answer for that. Next, INL, integral nonlinearity. Same curve, but different ways to calculate it. So remember, for the DNLs, we used the relative height, right, which is the increment height. But here is the absolute height, the difference from the absolute height, which is the output value, minus the reference line, so whatever the ideal curve is, just minus that value at that point, and it's going to be the INL. It's just different from so it's the absolute number minus absolute number. For DNL, it's relative number minus relative number, right? So it's just minus 1 LSB. Here's an example for that. Still a DAC. How can I tell it's a DAC? Saying it's a DAC in the caption. If the inputs are digital signals, right? The x-axis by default they are input. That's so that's a variable. That's a function. That's the output. And so again, so INLs are being calculated as the actual height. So whatever I got a point here, and the absolute value of this height of this point minus whatever it should be on the ideal curve. So it's actually the difference between these 2 points, this point and the ideal point on the ideal curve. It's just the distance between these 2 points. But so we just use this number minus here. So here it's labeled as the difference between these 2 points as 0.5 LSB. So that's the INL for that point. So INL 1 would be 0.5 LSB. That's the absolute height minus the ideal height. That's INL, integral nonlinearity. What is INL 0? 0. What is INL 2? Zero. So this is right on the curve. No error. INL 3. 0.5. INL 4. 0. INL 5. Negative 0.75 LSB. It's lower than the ideal point. INL 6, 0. INL 7, 0. Let's see if that's true. So INL 1 and 3, 1 and 3 are 0.5 LSBs. And INL 5 is negative. Okay. Any other things? No. Okay. Now ADCs. This is on page 948. How can I tell this is the ADC? Input values, not digital yet. So the output values are digital. And why at 0, there's no output. So see, at 0, so at some point in the middle, in between 0 and 1/8, why it's always 0? It's not jumping to any other intermediate values. So here's the output, the actual output of this 3-bit ADC, and that's definitely the ideal curve. So you can never get that smooth because there's a limitation on the resolution of the ADC. It's always having all the little steps. So which means for the analog inputs, it's only responding to these values, but any values in between 0 and the second one, it's not responding at all. So which means this ADC cannot resolve any of the values in between. So the resolution is low. If you have a better ADC with more bits or higher resolution, then you can imagine that there will be a lot of points on the x-axis. So have smaller stars compared to these huge stars. So you can resolve smaller changes. So this is not ideal, definitely, but we can find out the errors for this one. So for example, when it's 0, it is 0, so the error should be 0. And there's a concept called quantization error, which is different from INLs and DNLs. Keep in mind, quantization error is different from these nonlinearities. So quantization error is just the difference between the ideal value and the actual value. So you can see this curve, the dashed line, it's increasing. That's the ideal line, but actually the output of the ADC is not increasing at all. It's still flat at 0 during this time frame. So there are errors, and the errors in between these 2 points is going to increase when it's getting closer to 1/8 to the second point, right? Because you can see when it's at 0, 0 minus 0 is 0. But however, when the ideal curve is increasing, but the output is not increasing, so you can see the gap between the dashed line and the flat line is getting larger and larger. So you can imagine the quantization error, which is the ideal line minus the actual output of the ADC, is going to increase. It's going to be a linear line. So that's why it happens like this. This is a quantization error from 0 to this point. You can see it's increasing until it reaches this point. The output of the ADC is triggered. It jumps to this value. The quantization error just gets back to 0. It matches. Why it matches? You can see this output just hits this ideal curve, right? So the difference will be 0. That's why it's increasing, boom, like that. I can see the maximum quantization error is close to 1 LSB. Okay. So that's the concept of quantization error. I can plot it like this. Now, if you shift, so you can see here the quantization error is always larger than 0. So the average quantization error is kind of pretty large because it's always larger than 0 and bouncing back from 1 LSB, but it's always larger than 0. But if you shift the curve to the left by half LSB, compare this curve, the ADC output, compare this one to this one. So the difference is the second one just shifted the output, ADC output, to the left by half LSB. It's very interesting. So it's gonna reduce the average quantization errors. You can see it's going up to 0.5 LSB and going back to minus 0.5 LSB. It never reaches 1 LSB. Just consider as better performance. I'm also thinking about how to implement this on your SAR ADC. You know, I can probably find out a solution on that, which can, you know, boost the performance of the ADC. So they are all similar based on LT Spice schematics, and we have done that design in the summer. So I'm going to think about it, how we can shift it. So it's going to start from half LSB instead of 1 LSB. But anyway, so when we are just do the calculation, we are not thinking about the circuits, right? For now. So if you shift it, the quantization error will be smaller overall. And there will be some calculations regarding the DNLs and INLs for the ADC. So DNL for the ADC, definition, actual step width minus ideal step width. So the way I look at that is you can imagine you are just rotating this by 90 degrees. So it's like a DAC. And so for DAC, we also did step width, right? So or step height, but now it's width because you have to rotate it. So width and height is the same thing, just a length. And there are always, for both DAC and ADC, when you are calculating for DNLs, there are always actual minus ideal. And you're always looking at the digital input, the digital signal. So for example, DNL 0, imagine you are rotating this guy. So this, for the ADC, this is the width, but now this becomes the height. Okay, I'll rotate it back. But when you are thinking about it, just thinking about it this way. Okay, it's easier. So DNL 0 is expected to be half LSB. If we shift it, right? You are not assuming like we shift it, we're still expecting 0. It's not. So we're expecting half LSB. So the actual height or width, you can look at this point. The actual width is half LSB, and the ideal one is also half LSB. So actually the DNL 0 is 0. The DNL 0 is 0 LSB. Let's see if that's true. See? DNL 0 is 0. Yeah, because we shifted. So that's what we expect. What about DNL 1? So you want to look at the height. If you rotate it, you are looking at the height. So here's the height. Right? If you rotate back, it becomes a width. So what's the actual width here? The actual width here is 1 LSB. See, from half to half, it's still 1 LSB. And ideal width should be 1 LSB as well. So there's no DNL. So DNL 1, you're looking at the digital data here, the label. DNL 1 is 0. DNL 1, 0. Next, what about DNL 2? Looks wider, right? And you can see it reaches this point. So it's 1.5 LSB minus what? 1 LSB. So DNL 2 will be 0.5 LSB. Where's DNL 2? Next page. So DNL 2, 1.5 minus 1, 0.5 LSB. Still look at the digital number, DNL 3. Little tiny change, 0.5. So 0.5 minus 1 will be negative 0.5 LSB. Next, DNL4, the right size, 0. DNL4, 0. DNL5, negative 0.5. Right? DNL6, 0.5. Oh. 0.5. DNL7, DNL7. No, DNL7 is supposed to be, because you shifted everything to the left, so DNL7 should be 1.5 LSB. And 8 is 1.5. See, since the ideal step width is 1.5, and now it's actually 1.5. Why should be 1.5? This point should be here, but now you shift it to the left. So it makes this one longer, right? Okay, so we have 4 different types of calculations. Now we are done for 3 of them. Last one, INLs for ADC. Integral nonlinearity. It's on page 952, example 28.7 on the textbook. Remember INLs? So DNLs are actual step height or width minus the ideal step height or width, right? And INLs are the absolute height or width minus the ideal, whatever the ideal point is on the curve. So look at this curve. The dashed line is the ideal one. And starting from INL 0, INL 0, 0, INL 1, because this point is right on the curve, so there's no error. It's on the ideal curve, cannot argue about anything, right? This is also 0. Or this one. So NL3, if you rotate it, we're not going to rotate it, but if you can imagine you are rotating the paper by 90 degrees, you can see that this point is right here at here. But now it actually should be on this dashed line, but now it's here. So it should be the real one minus the ideal one. So should that be positive or negative? Positive, because it's higher, right? Rotate it. See this point? This point is higher than this point. And you are just calculating the difference between these 2 points. The distance between these 2 points is very simple. Just calculate the difference, the gap between them, right? And that will be positive. And now you look at the x-axis. This is, just use this number minus this number, right? Just, it's going to be this. Eventually it's 0.5 LSB. And you are getting this value, and you have to convert it into something LSB for the answer. So this NL is 0, definitely, and this is also 0 because the point is right on the curve, and this is not. So the ideal point is higher than this point. And you can see it should be negative 0.5 LSB. And the last one, INL7, is right on the curve, so it's 0. Simple, right? Great. Yeah, let's just lay out some of the concepts of the ADCs, and I think we're going to do the quiz. It covers the structure of the STAR ADC starting from Friday. Yes. So there are several concepts regarding ADCs. First, the sampling, just sampling, right? Sampling. What is sampling? Sampling means it's measuring signal at periodic time interval. And there's a theorem called Nyquist-Shannon sampling theorem. So the sampling rate has to be larger than or equal to twice as much as max frequency of the signal. Because some of the signals have different frequency components if you do a Fourier conversion transform. So for example, the signal like this, right? It has different frequency components in the signal. So the maximum frequency in this component is F max. If you do a FFT, you're going to see different components. Frequency component has a different intensity. So this will be max, F max. If it's a pure sine wave, it's just one frequency. It's just one frequency is the F max. So the sampling rate has to be larger than twice as much as the max frequency of the signal. Important, okay? To know that. The reason is if your sampling rate is very low, but the frequency is higher than your sampling rate, which means you are sampling, for example, this point, and I sample this point again, and then I sample this point, and sample this point, you cannot recover the original signal. So the ADC cannot see this sine wave because it's not sampling these points. It's only sample this point, this point, this point. So it's thinking like this is a line, not a sine wave. So it has to be, the frequency, sampling frequency has to be larger than twice as much as the maximum frequency, which means it has to sample like here, like this. It's 4 times larger than that. But this is, it doesn't mean that you can use it 2 times F max. It's just saying like it cannot be lower than that. Lower than that is going to be awful. So it has to be, ideally, usually it's 10 times or 100 times faster than that. You can get a decent recovery of the signal, right? You just need to know this 2 times F max. Aliasing. So introducing of false frequencies. In the process of sampling. If you have a low sampling frequency, you are going to see aliasing in your recover signal, because you cannot recover all the frequencies of the original signal. It's giving you a line. The frequency will be totally different. There's no such a signal with that frequency in your original signal. Okay, just some concepts you need to know. And yeah, I think that's it for today. I want to give you some time, like 20 minutes to work on the quiz. And the quiz is not difficult, but I hope you guys can, you must show the process of the